Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are on lecture 15 today and we are discussing contact mechanics, and you will remember that we have so far not included adhesion in our formalism, but we are going to do that shortly. So, in the last lecture I had discussed about this loading on a triangular area of contact. We discussed about uniform load over the whole area of contact, and then we found out that what should be the vertical deformation at a point O, that is here, which is within the area of contact or area of loading of this triangle, and let us say if this point C which is away from it. And so, we deduced these relations. So, in the today's lecture I am going to discuss little bit more about this loading over a triangular area, but in a slightly different manner, and then I will start what is known as the Hertzian mechanics and contact between two deformable bodies, and here also we will discuss without adhesion or any interactions. So, friends, we have discussed about loading over an triangular area of contact. So, let us say today we discuss about loading on the shaded area which has got an arbitrary shape, and because of this loading in the shaded area, what is the vertical deformation at this point of point B, that we will like to know. And we will see here that the results that we derived for the triangles, okay, that will be useful over here. So, I will just draw a few triangles. So, for example, I will extend this line here, and I will need to extend this line here, and I will like to draw a perpendicular here, I like to draw a perpendicular here, I will like to draw a perpendicular here, I like to draw join these two lines, I will like to join these two lines, and I will need to draw a perpendicular to this particular point. So, here you will see that we have in a sense we have made several right angle triangles, and so we will use the idea of superposition, okay, to find out the vertical deformation at B. So, for example, let us say that this G F D E F G, this is the area through which the force is it is loaded, and I have drawn these perpendiculars as I just did it in the last slide, and here these are joining lines and the perpendiculars, and here you can see that this right angle triangle, this is let us say E H 1 B, okay, E H 1 B here, and then let us say this triangle, that is E H 2 B. So, that is this triangle over here, and then we have this F H 2 B. So, F H 2 B is this triangle, this whole triangle over here, and then I have this F H 3, this should be F H 3 B, I am sorry about that, F H 3 B, that means this triangle. So, this will be the whole area, okay, under all this from this point B to H 3 to G, F, E, D and H 1. And now, this is not the whole area at which the load is applied, rest of the it has to be subtracted, so the load has to be subtracted from the rest of the area. So, that means that the positive load is being applied over this triangles, and the negative load is being applied on these triangles. So, these triangles are D H 1 B. So, that means here this is this area, and then it is this area, this B H 4 and D. So, that is D H 4 B, it is this area, and then G H 4 B. So, that is this area G H 4 B, and then B H 3 G. So, that is this area. So, in essence, in one kind of calculation we think that the positive load is applied over these triangles, and these are all right angle triangles, and then negative load is applied on these triangles which are again right angle triangles, and we have already deduced the results, okay, for this right angle triangle loading for a right angle triangle and on a point like this. And so, therefore, we extend those ideas that we have deduced in the previous lectures, and we use those results over here and use this principle of superposition to find out the deformation at this particular point B. So, that is the idea. Now, friends, what is the question arises that why am I interested in doing all this? So, the motivation comes from something like this. You see, these are these different insects and bugs, and they have got adhesive pads at their feet, and using these adhesive pads they can adhere to surfaces of different types, smooth surface, rough surface, wet surface, dry surface, surface having different types of roughness, chemical character, and so on. And scientists have found out that the adhesive pad at the feet of these animals are of different shapes, and they have evolved also through different routes. So, these arrows represent here the evolutionary path, and then you see here that some point of time there was spherical shaped adhesive pad, then there are conical shaped, and there are filament like. Here the surface is completely flat like this bush cricket, and then this particular bugs has this toroidal shaped adhesive pad, then there are suction cups and all like that. Now, the question is that how does this different shapes and sizes and number density of these adhesive pads that help these natural organisms to adhere to different surfaces. And in order to know that, we need to understand the contact mechanics of this kind of shapes on a given surface and like that. And so, therefore, we need to understand that we need to study a little bit more systematically how this what is the stress profile that appears below this contact point, and that is why we actually studied all the things that we did so far. Only thing is that we have not understood, or we have not incorporated adhesion in that. Now, adhesion and non-adhesion, as far as contact mechanics is concerned, it is just the opposite way the force is applied. So, in the case of indentation, we apply the compressive load on the elastic hub space, and in the case of adhesion studies, we apply the pulling load. So, we will soon examine, at least for some of these geometries, what should be the pulling load if suppose and surface is in contact with this adhesive pad, and you are trying to apply the pulling load, what kind of force will be required to get over adhesion strength at the interface. So, we will come to that. So, this is mainly and here also you see that this adhesive pad from the top it requires a hexagonal pattern. So, that means it appears that the spherical or circular structure or maybe rectangular structure may not be the optimum structure for adhesion on a surface. It is this kind of rectangular or maybe somewhat more arbitrary shape that may be more suitable. So, we in order to do that, in order to understand that only, we developed all these formalisms, and now using those formalisms one can actually further work on this kind of surfaces or this kind of shapes and sizes, and then get analytical and not analytical numerical results and all that. So, with this background today, so basically the questions that will be needs to be asked and people will be interested in asking is that why adhesive pads have to revolve in certain shape for an insect species, or let us say what are the advantages of certain specific shape of the given condition, what is an optimal shape, or let us say how the coupled effect of shape of adhesive pad and their number density results in strong adhesion in variety of environments. What are the basic differences in pressure distribution or stress singularity in these different cases. So, these are the questions that an adhesion scientist will be interested to know, and we have developed the formalism for that. So, today I will like to discuss another topic which is about contact between curved surfaces, and it is known as the Hertz mechanics, and Hertz was the person who developed these ideas or this theory, and therefore it is called Hertz mechanics. So, it is about contact of two non-conforming solids. So, non-conforming solids are something like this. Suppose you have got one curved surface and then you have got another curved surface, and you bring them in contact, and so at the no load condition, that means when the load on them P is equal to 0, that is contact load is 0, there is actually point contact. So, there will be point contact or a line contact okay, if they are elongated element or object. Okay. So, this is a point contact non-conforming solid. Now, on the other hand, there are many mechanical or engineering applications where let us say we have got one surface here like that, and let us say there is another surface like this, okay, which is actually showing some kind of like mechanical behavior or some applications, rotation or whatever. Now, in that case, at the zero contact load, the contact area is not a point, that is a finite contact area is there. Okay. So, they are called conforming solids. So, what we are going to discuss about here today is non-conforming solids, and when we discuss non-conforming solids, it is not necessary that the surface or of the solid has to be convex like that. No, it is not necessary. It can be convex, it can be concave, okay. It can be one convex, one concave surface, but at the end of the day it has to be non-conforming solids. That is all is the requirement. Now, this solids, there are some examples here. Let us say sphere is in contact with a solid plane surface. So, at zero load there will be finite point, a single point contact, or let us say this is an ellipsoidal surface or like that. But in all these cases, okay, at zero load, that is a point contact, and as we apply more load, the contact area increases and there is a finite area that appears. So, this is the example of conformal and non-conformal. So, I have already discussed this. So, what is happening is here is this contact of two non-conforming solids. Initial contact between the solid is a point or a line at a zero load. At the line is when, suppose you have got a cylinder over here, a cylindrical surface over here, and let us say there is another cylindrical surface over here like this, and when you bring them in contact, then because of this, when they contact without any load, then the contact will be a single line or like that. So, that is why we will have line at a zero load, okay. But slightly increased load, this there is deformability of this by objects, and so there will be contact over a finite area. So, other thing is that when we discuss this Hertzian mechanics, we also consider that the dimension of this contact area which forms after when you apply the load will be much smaller with respect to the two bodies that we are considering. So, that means that these two bodies, okay, will be quite large with respect to this diameter of the radius of the contact area, and of course, the surface topography is smooth both at macro and micro scale. So, that means this contact area is completely smooth. So, what happens with most practical surfaces, the surface looks optically so smooth in the one particular scale, but if you show the microscopically, you will see there are this kind of like roughness features. No, we are not discussing about that kind of surface, we are discussing about completely smooth surface, okay, so that the within the contact area the load is continuously distributed or goes from one place, one body to another, okay, without any partition like that. So, that is very important over here for that is for assumption here for this theory. And then, so there is topography smooth and macro scale, both macro and the micro scale. And next is the frictionless contact, means like these two bodies when you apply load on them and they come in more and larger contact area, okay, there is no friction between them, okay. So, this the deformation that happens at the surface, okay, without any friction, without so it has the full degree of freedom to deform horizontally or like that. So, these are the basic assumptions, and I will discuss some more assumptions that comes as we come, but let us see that what happens. The profile of the each surface at the vicinity of the origins, means like these two surfaces let us say has been brought in contact at a zero load. So, there is a point contact over here let us say or line contact. So, how does the profile look like at the vicinity of the origin, okay, that is what we are saying. So, what we will say that the profile looks like parabolic. So, that means that let us say Z1 will be some A1 and then x square plus A2 y square, okay, plus let us say A3, okay, xy or something like that, or so it is like this. So, basically we write it not A1, we write it A1, B1 and C1. So, let us say Z1 is represented as A1 x square plus B1 y square plus C1 xy, and Z2 represent as A2 x square plus B2 y square plus C2 xy like that. So, this is basically parabolic profile, and this Z1 and Z2, that is being measured from where? Measured from a plane over here that goes through the origin or the point of contact of these two surfaces. So, this particular point, it goes something like this. So, that is the plane there that goes through this particular point O, and we measured from this particular point the Z1 and the Z2. So, these are given by these two equations. Now, little bit about the surface, okay, how we can define it. So, orient the axis to eliminate the term like xy. So, what it means is that suppose we have been given this particular surface and xy, and this is, and we represent this surface by this particular equation, z1 is equal to a1 x square plus b1 y square plus c1 xy. So, what we can do is that we can orient this x and y axis such that now we will have z1 will be equal to, this is x1 x square by 2 r1 dash plus y square or x1 square y1 square by 2 r1 double dash. So, we can represent it like that. And what are this r1 dash and r1 double dash? So, these are actually principal radii of curvature. So, any surface at a point on a surface, we can think of several different radius of curvature at different planes, right. But then there are actually two planes which are perpendicular to each other, at which the radius of curvature are maxima or minima. So, these are called the principal radius of curvature, principal radii of curvature. So, here these are this principal radius of curvature. Now, we can have this other surface also, we can write it like that. Now, here for example, this maximum curvature, minimum curvature of all cross sections of that point. So, for example, here this is the curved surface, let us say this particular point. So, at this point we can think of several different radius of curvature at different planes, but then we have two different cross sections or planes at which the in one case the radius of curvature will be maximum, another case it is minimum. So, we need to take those two. So, these are let us say called maximum and the minimum curvature. So, here for example, for the sphere there are the maximum minimum curvature are equal, right. So, basically if this is the cross section, so in this cross section this is the radius of curvature, and the other cross section there will be other radius of curvature perpendicular to that. So, that is actually r1 by r2 is equal to a. Similarly, for this case cylinder, so the maximum radius of curvature, that is the larger one, so that is all r2 will be infinity, okay, and r1 will be equal to a. So, it is like that. Now, this particular surface for example, so here, okay, one can cut these two planes which are perpendicular to each other, and one can see that one is this r1, that is a smaller one, and the r2, that is the larger one. So, these are the principal radius of curvature. So, like that for any surface, okay, one can actually find out this principal radius of curvature. So, there are mathematical tools which are available which are not part of this course, so I am not going to go into that. Okay, so, we will discuss about regular objects in the sense that let us say sphere or cylinder. So, cylindrical curved surface or sphere curved surface of the sphere, that is why we do not need to worry about the other geometries or finding out the principal radius of curvature for other cases, but it can be done. So, now if the for the second surface similarly we can write it z2 is equal to minus of 1 by 2 r2 x2 square and plus 1 by r2 double dash y2 square. This minus sign because that plane that I was telling you, that this is the plane. So, in one case this is positive, another case this is negative, and so that way it is minus, as minus sign has to be there. So, that is the reason. So, now what we can do is we can find out that let us say that is a common axis xy axis. Now, at that common xy axis, okay, what is the gap between these two points? So, let us say at a given point xy, what is the gap between that? That is all we like to find out. So, for example, over here let us say this is the common point x1 x2 axis and there, okay, this is z1 and this is z2 at this particular point. So, what is the gap between that? So, that gap is let us say h. So, h will be equal to z1 minus z2, okay. So, that is the way. So, z2 is negative, so that h will be positive anyway. So, z1 is positive, h2 is negative. So, z1 minus z2 will be positive, and that can be represented as by this relation. So, exactly, so what actually happening, this ax square plus by square plus cxy, so that defines contours of constant height. So, in essence let us say that this is a surface, one surface, this conical surface, and on this is the flat surface. Let us say that we are finding out the height of this conical surface at different points, right. So, let us say this height. So, now what is this height over here? So, at this height we have all these rings. So, these circles that we have there is a contours of constant height. So, one is for let us say c is equal to 3, that is one height, and c is equal to 4, c is equal to 7, c is equal to 12, like that. So, at this different height, okay, what are the contours of this gap of the constant gap between these two surfaces, that is represented by this contour plot, right. And so, here that contour plot, okay, we write it like this, ax square plus bay square plus cxy. Now, what we do is we orient this xy axis in such that we will have only x this square terms, x square and b square terms, this c term, okay, that will become 0. So, we orient the xy axis in such a way that the c vanishes. So, basically what we have now is h is equal to ax square plus by square, and where this term a can be written as 1 by 2 r dash and 1 by 2 r double dash. So, what are these quantities? So, these are called r dash and r double dash, these are called principal relative radii of curvature, principal relative radii of curvature. So, x1 axis is principal radius of curvature of surface 1 and x2 is the principal radius of curvature of surface 2, like that. And so, that was the earlier case, and now the principal radius of curvatures we have already defined earlier, and now this so we already have the r1 and r2 and all that, and the angle between those principal radius of curvatures for this over here, this here this x1 y1 and this x2 y2, okay. So, this is one set of x1 y1, this is one set of coordinates here, and x2 y2 this is another set of coordinates here. So, in this x1 coordinate this surface 1, okay, that is the principal radius of curvature occurs, and x2 y2 in this case the principal radius of curvature occurs for surface 2, and principal radii of curvature are given as r2 dash and r2 double dash. And now, we have this principal relative radii of curvature, okay, which is at which this c term is 0 over here, and so we have this term relative radius of curvature r dash and r double dash, and this r dash and r double dash, these are can be expressed in terms of this r1 dash and r2 dash and r1 double dash and r2 double dash, and that is what we are writing over here. So, here this a plus b is equal to 1 by 2 r dash plus 1 by 2 r double dash, and that can be written as something like this. Relations can be derived, and this has been derived, and so one can derive, I am not going to go into that. And then b minus a, so that can be written as like this, 1 by r1 dash minus 1 by r1 dash whole square plus 1 by r2 dash minus 1 by r2 dash double dash whole square, and then this particular term with the term cos 2 alpha and the square root term, okay, like that. So, this is the way. So, this has to be positive. So, therefore, the absolute values of b minus a, that needs to be considered. Now, what do you do with this? So, what do you do with this is this, that if we know what is this r1 dash, r1 double dash and r2 dash and r2 double dash, okay, we can, and then the angle between these two sets of coordinates, right, this angle alpha between these two sets of coordinates, we can find out what will be the relative radius of curvature of r dash and r double dash, that is what we can find out. And because we have two unknowns r dash and r double dash, so we need these two equations over here, and we can actually find out. And we can also find out that show that this depending on this r dash and r double dash, it will be an ellipse, and this ellipse will have this ratio of the length of axis given as this, okay, b by a square root will be equal to r dash by r double dash square root. So, we will give some example here. For example, let us say there are two cylindrical surfaces each with radius r, okay. So, each has got the r1 dash has an r2 dash, both are equal to r, and since they are a cylinder, so the other radius of curvature will be infinity, okay, that is the line actually. So, it is infinity there. So, we have, and let us say these two cylinders are oriented like this. In one case their axes are parallel to each other, right, and so therefore, the angle between these axes are actually 0. In another case, let us say they are perpendicular to each other. So, they are placed normal to each other. So, therefore, the angle is 90 degree over here, and then there is an intermediate case at which this is at angle 45 degree or like. Now, what will be the gap look like, this contour of this equal gap between the surfaces will look like. So, by we can use our common sense, and that will suggest that suppose if I look at from the top, I will see here okay, as a rectangle, I mean like something like this rectangle for this case over here. On the other hand, if I look at from the top, I will possibly look something like this, an ellipse, and if I look at from here, I will actually get something like this circle. So, we will prove that is the case by some small example. So, let us say two cylindrical surfaces of each radius r1 dash r2 dash is equal to r, and r1 dash r2 double dash is equal to infinity, and let us say the angle between them is 45 degree. So, this angle between them is 45 degree. Now, what happens? 1 plus a by a plus b will be something like this. Okay. So, here this for example 1 by 2 here and 1 by r here and 1 by r double dash, this is equal to 0 here, this is also equal to 0 here, and this is equal to r here. So, 1 by r. So, this is equal to 1 by r, and over here this is equal to 0, this is equal to 0 here, this is 0 here, this is 0 here, and remember cos 2 alpha is equal to cos of 90 degree. It will be cos 90 degree because alpha is 45 degree, cos 90 degree is equal to 0 here. So, this term actually equal to 0, and so therefore, we have half here, and then over here it will be 1 by r square plus 1 by r square, it is 2 by r square. So, it is 2 by r square, and this is square root. So, it is 1 by square root into 1 by r, something like that, and so therefore, we can estimate, write it as a plus b is equal to 1 by r, and b minus a 1 by square root of 1 by square root 2 1 by r, and from there we can get this term r dash and r double dash, because we know that a is equal to 1 by 2 r and b is equal to 1 by 2 r dash and b is equal to 1 by 2 r double dash, and so therefore, from there we can get this r dash and r double dash. So, we can use your calculator and you can get it to be 3.42 r here and 0.585 r here. So, we can get what is defined, what is known as this quantity called equivalent radius, which is given by this r dash r double dash square root. So, we get it to be r by square root of 2. We can get also a ratio of the major and minor axis. So, that is not 1, that is different. So, it is 2.41. So, it has to be contour has to be an ellipse. So, we can get an elliptic contour because of that, for example something like this. Now, here these are the interference fringes. So, if you use monochromatic light and like to see from the top, you will see this kind of fringes very close to the for a small gap between these two cylinders. Let us say that the angle between them is alpha is equal to 90 degree. Okay. So, in that case we have got again this will go, and cos 2 alpha is cos pi will be minus 1, right, and so this also goes, this also goes. So, we can simplify this now, a plus b will be equal to again 2 by r. So, this is a by r, and this is b minus a whole square, that will come out to be 0 here, and so here you will see a is equal to 1 by 2 r, b is equal to 1 by 2 r, and so therefore, r dash and r double dash both are equal to r here, and therefore, we get this, the contour will be equal to a circle. So, here contour will shows a circle, and if you see from the top using and monochromatic light and optical microscope, maybe we can get this kind of fringes which will be circular fringes. So, I will stop here and I will take up the further discussion next lecture. Thank you.